Okay, remember what a function is. A function f from a to b is a rule of correspondence that assigns each element in a to exactly one element in b. And we call a the domain and b the range. In other words, we've got an input and we've got an output. But what happens when we swap those? What happens when we make the domain a the range and b the range the domain? We swap those. In other words, what happens when we swap all the x's and y's in all the ordered pairs? Well, it's possible that we get another function that still follows this definition, and we call that the inverse function. So let's take a look here. Let's suppose we've got a couple of functions here, and these are the ordered pairs. Okay, so we've got -2, 4, -1, 1, etc. And over here we've got -2, 8, -1, 1, -1. And those correspond to the x squared function and the x cubed function. Now, these are two functions. Now, let's suppose that we swap the ordered pairs. Okay, so notice what I've done here with this one. I've taken the y's and made it the x's, and I'm going to take the x's and make that the y's. Now what we've got here is another relationship. Now this over here, this first one, that's definitely a function because every x corresponds to exactly one y. But let's look at this, what happens when we swap the ordered pairs. Well, notice that this 4 corresponds both to a -2 and to a 2. So right away, this is not a function. Okay? It's not a function there either. In other words, so we see two examples here where we have an x corresponding to two y's, one in -1, one and 1. So this is not a function. This is, when we swap the ordered pairs, that's not a function. And what we do is we say, okay, this graph, the graph of x squared, that is not a one-to-one function. In other words, every x corresponds to exactly one y, but not every y corresponds to exactly one x. When that happens, we say we have a one-to-one function. Now let's look at this other one, this x cubed. And let's swap the ordered pairs on this one as well. The y's over here become the x's here, and the x's here become the y's. Now, notice that in both cases, we do have a function. This over here is a function. Every x corresponds to only one y, one and only one y. And we say when this happens, we have a one-to-one function. And this right here, this is the inverse relationship right here. These are points in the inverse function. This is the original function. This is its inverse. Now, graphically, what does that look like? Let's think about some points. We'll just plot some points on the x cubed. Okay, here's some points. Now, I'm going to swap the ordered pairs. This 2, 8 becomes an 8, 2. Okay. And so I went ahead and plotted that point. This -2, 8 becomes a -8, -2. So I'll plot that point. And now if we sketch these, or actually interchanging the x's and y's here makes no difference, but let's just do a quick sketch of the two graphs. Notice here's what they look like. Now this right here, this is the line y equals x. And notice that when we graph these two functions, we got x cubed and we've got its inverse here in yellow. Notice this line y equals x is like a mirror. It's like a mirror image. The function f, it's like it's reflected across this line y equals x. Okay? You have symmetry. I guess I was looking for the right word. You have symmetry. Okay? So functions and their inverses are symmetric across the line y equals x. Now, here's another property that these inverses will have. And if this happens, if you have f of g of x and it equals g of f of x, then and they equal, both of those things equal x, then f and g are inverses of each other. That's what that means. That only happens if the two functions are inverses of each other. So let's suppose we have f of x equals 2x and g of x equals 1/2 x. And we're wondering, are these inverses of each other? Well, let's find f of g of x. Well, I take the 2x, but in place of the x, I put 1/2 x. And notice the 2's cancel, and I get an x. Now let's go the other way, g of f of x. So I take 1/2, but instead of x, I put 2x. And notice I get an x. That means that f of x and g of x, they're inversely related. So we could say that g of x is really equal to f inverse of x. Now, let's look at this one. Here we've got f of x equals x cubed, g of x equals x to the 1/3. So I'm going to find f of g of x. That equals x. Let's find g of f of x. That equals x. So it turns out that f and g are inversely related. The inverse of f of x is g of x. And we write that this way sometimes. Now, notice that this right here is read f inverse of x. Now, this is not f raised to the negative first power. This is not 1 over f of x. In mathematics, you have to use context sometimes. And the context here is we're dealing with a function, and this, whenever you're dealing with a function, you see this -1 like this, it indicates it indicates inverse. So this f inverse of x, that's the inverse of f of x. Now let's look and see how, if we're given a function, how we would find the inverse. So we'll use this example here. We have f of x equals x cubed minus 5. Now the first thing we do, we change notations just because we're about to pour a little bit of algebra on this thing, and we don't want to have to lug around that bulky f of x. So we change it to y, and then we interchange the variables. Every place we have a y, we replace it with an x. Every place we have an x, we replace it with a y. Now at this point, we've got the inverse relationship here, but that's not the way we're used to looking at a function. We're used to seeing y equals something. So let's solve for y. Okay, so I need to add 5 to both sides, and then I take the cube root on both sides, and I get y equals the cube root of x plus 5. Then we change notation back to indicate, okay, this is the inverse. So we have f inverse of x, that's the inverse of f of x.